today's session we are going to discuss about unsteady state heat transfer. That is, in that we are going to understand lumped system analysis or lumped heat capacity systems. So in this session we are going to understand unsteady state heat conduction after completion of the session. Actually, heat conduction, so far whatever the heat transfer we studied is steady state heat conduction. So heat conduction generally divided into steady state heat conduction and transient heat conduction. So what are the difference between the steady state heat conduction and unsteady state heat conduction? Steady state conduction, actually heat transfer does not vary with the time. The heat transfer can vary only with respect to location. If you see unsteady state heat conduction, in unsteady state heat conduction or transient heat conduction, heat transfer varies with respect to time as well as location. If you look at the diagram, you can understand the first diagram 15 degree centigrade and it is reduced to 7 degree centigrade. The heat flow is constant in both the diagrams. If you look at the second one, the time is 2 p.m. in the second diagram time is 5 p.m. So you can find the temperature reduction. 15 degrees reduced to 12 degrees centigrade, 7 degrees reduced to 5 degrees. That means with respect to time, heat is getting varied. That is called transient or unsteady state heat conduction. Introduction: generally in unsteady state heat conduction, heat flow vary with respect to time. The temperature distribution at any point of the system vary continuously with time. Applications are examples of transient heat conductions. Generally, transient heat conduction occurs in cooling of IC engines, automobile engines, heating and cooling of metal billets, and heat treatment of metals by quenching, brick burning, vulcanization of rubber and all. And particularly it is applicable in food processing industries. So pasteurization of milk, freezing of food, so all comes under lumped system analysis or unsteady state heat conduction. So the temperature fields in any transient case in general is given by temperature, the function of location as well as time. So temperature is equal to f of x, y, z, t. Unsteady state problems can be broadly divided into 4 categories. One is lumped system and infinite thermal conductivity. That is what we are going to see now. Second one, finite conductivity and convective resistance. Semi-infinite solids, that is third one. Fourth one, periodic variations. And let us see how the lumped system works. So all solids have finite thermal conductivity and there will be always temperature gradient inside the solid whenever heat is added or removed. So however, solids are of large thermal conductivity with surface areas that are large in proportions to their volume, like plates and thin metallic wires. The internal resistance, generally L by Ka, can be assumed as small or negligible in comparison with convective resistance 1 by Ha. You know very well, internal resistance of a body is indicated by L by Ka. The convective resistance is indicated by 1 by Ha at the surface. So when internal conductance, there is no internal conductive resistance, that means there is no resistance for conduction, then it should be 0. That means if it is assumed to be negligible, then the system is called as lumped system analysis. So typical example, heat treatment of metals, time response of thermocouples and thermometers, etc. The process in which internal resistance is assumed to be negligible in comparison with its surface resistance is called Newtonian heating or Newtonian cooling process. The temperature in this process is considered to be uniform at given time. Such an analysis is lumped parameter analysis or lumped system analysis, whatever it is. The whole solid whose energy at a time is function of its temperature and total heat capacity is treated as one lump. That means internal resistance, when it is assumed to be 0, there is no internal conductive resistance, only convective resistance will be available. So that means the temperature should be uniform throughout the entire mass of your body. For example, when you take a copper ball, if it is heated to certain temperature, for example 800 degrees centigrade, if it is heated, then after a certain period of time, if the hot copper ball is left over the environment with 800 degrees centigrade, then slowly the temperature is getting reduced. That means heat transfer takes place with respect to time. Slowly the temperature is getting down from 800 degrees centigrade to 750 degree, 700 degree, 650 degree, 600 degree, like after certain period of time it reaches the environment temperature. So here in lumped system analysis, so throughout this process the temperature throughout the solid is assumed to be uniform. That means the temperature should be uniform throughout the entire mass. So when internal resistance is negligible, the temperature inside the solid is uniform wherever at any point of mass. If you see this slide, you can understand the difference between which is lumped system, which is not lumped system. See, there are two examples. During transient heat transfer, the temperature normally varies with the time and as well as position. So in the special case, variation with time but not with the position. If you see, the first diagram shows a copper ball with internal resistance, internal conductive resistance is assumed to be negligible. So throughout the copper ball we are seeing only 70 degrees centigrade at any point. So 70 degrees centigrade, that means the temperature is uniform throughout the solid. But if you take a roasted beef, inside the temperature, inside 1.40 degrees centigrade, other point 90 degrees centigrade, 110 degree. So if you take the outer surface might be roasted properly, but inside it has not been roasted, so it cannot comes under lumped system analysis. So you must understand the applications of lumped system. You must differentiate which is lumped system, which is not lumped system parameter. Now let us derive the governing equation for lumped system analysis today. Let us consider a body whose initial temperature is Ti throughout and which is placed suddenly in ambient air. Now you can see the diagram. So we are assuming a body with negligible internal resistance and the initial temperature is Ti and atmosphere temperature is assumed to be Ta. It is shown in the picture. The transient response of the body can be determined by relating its rate of change of internal energy with convective exchange of the surface. That is, amount of heat or amount of heat stored in the body, if it is released as convective heat or if it is released as convection, the energy stored in the body is equal to amount of energy convected. So that means how much energy is stored in the body, that is mCp del T. If you take here for example m, see here mCp del T. So I can write it as mCp dou T by dou T. So dou T is with time, this T is temperature. So mass, so instead of mass I can write this as rho Cp. So V rho Cp, sorry, So instead of mass I can write rho Cp. So rho V, so mass by volume is equal to density. So m can be written as rho into V. So the equation you are seeing like this, right? So let us see the equation. So the amount of heat released from the body is equal to amount of heat convected, or amount of heat stored in the body is equal to amount of heat conducted. The minus indicates that heat is rejected from the system. So now this rho is density of the solid in kilogram per meter cube, V is volume of the body in meter cube, C is specific heat capacity of the body in joule per kilogram degree centigrade, H is unit surface conductance or heat transfer coefficient between the solid and environment or solid and air. Suppose if it is left to a water bath, solid and water. T, temperature of the body at any point time in degree centigrade. A is that is surface area of the body in meter square. T, ambient temperature or atmospheric temperature. T is the time. Now after rearranging the integrating the above equation, let us see once. See, sorry, the Q is equal to minus rho AV dt by dt. This equation, if it is rearranged as like this, because this dt divided by this T minus TA can be brought to down. So dt by T minus TA is equal to minus HAS, the minus will come this side, and rho Vc integration of d tau. So now we are integrating both the sides, dt by dt. So when you differentiate anything, if it is in the form of dx by x, so you can write it as ln t minus ta is equal to, the terms will come, C1 is integrative constant. Okay, when dt becomes t, so C1 is integrative constant. Now here the boundary conditions are at initially when time is 0, the temperature of the body is Ti, initial surface temperature Ti. So by applying these boundary conditions in the previous equation, let us go to previous equation. So when T is 0, then time T is 0, that is tau here, this term becomes 0, So C1 is equal to ln of, instead of T is equal to Ti, right? So when time tau is equal to 0, this terminology becomes 0, then this temperature becomes Ti. So C1 becomes ln of Ta minus Ta. See, let us see, that is what we got here. C1 is equal to ln of Ta minus Ta. So when you substitute this in that previous equation, ln of T minus Ta is equal to minus HAS divided by rho Vc into tau plus ln of Ta minus Ta. This is the value of C1. So now by rearranging, when you bring this ln Ta minus Ta in this side, so automatically by using ln logarithmic laws, T minus Ta divided by Ti minus Ta. Here T is temperature at any point, Ta is atmospheric temperature or air temperature, Ta initial temperature of the body, Ta atmospheric temperature is equal to exponential of, because when you remove ln here it becomes exponential of this term, so minus HAS into rho Vc into tau, So now the above equation gives, this is the governing equation for lumped system analysis. When you assume internal conductive resistance is negligible, then this equation is the governing equation. So the quantity rho Vc by HAS, actually here HAS by rho Vc, the quantity rho Vc by HAS is called as thermal time constant. It is called as thermal time constant. Okay. So you might have understand how to derive the governing equation for lumped system parameter. So now let us see. I am going to introduce a new non-dimensional number which is related to the unsteady state conduction. Before that, we should understand what is meant by characteristic length. Here characteristic length is defined as volume of the solid with respect to surface area of the solid. So we can define characteristic length for different types of objects, because heat transfer can take place any types of any shape of the solids. Particularly lumped system will take place in any shape of the solids. So but we can generalize few types: flat plate, cylinder, sphere, cube. For flat plate, characteristic length is equal to volume is V divided by AS. Volume is length into breadth into height of the flat plate. Surface area is 2 into breadth into height. So L by 2, when you cancel all the things, L by 2 will come. So for cylinder, pi r square L, that is volume, surface area 2 pi r L. So when you simplify, R by 2 will come. R by 2 is radius of the cylinder. For sphere, characteristic length can be defined volume to surface area ratio. So volume of the sphere 4 by 3 pi r cube, surface area 4 pi r square is equal to R by 3. Now cube, for cube, so L volume is L cube, surface area is L square into 6 phases, right? So it becomes L by 6. L by 6 is the characteristic length. Now let us introduce a non-dimensional parameter which is more relevant to the lumped system analysis, that is HLC by K. Just before we have discussed about characteristic length LC. Here HLC by K is called as Biot number. So Biot number Bi is equal to HLC by K. It is given an indication. It is defined as the ratio of internal conductive resistance to the surface convective resistance, or internal resistance to surface resistance. So when the value of Bi is very small, it indicates the system is as small internal resistance. That means if Biot number is less than 0.1, then the system can be assumed it as lumped heat capacity system or lumped system analysis, or it is coming under lumped heat capacity system. So we can go with the lumped heat capacity approach to advantage with the simple shapes such as plates, cylinder, sphere and cubes. So the error associated is around 5%. The non-dimensional factor alpha T L square is called Fourier number. This is another number which signifies the degree of penetration of heating or cooling effect throughout the solid. So this Biot number gives the ratio of internal resistance to surface resistance. Fourier number gives the degree of the level of penetration of heating or cooling effect through the solid. So this lumped system can be applicable for cooling of solids as well as heating of solids, because when you take a watermelon from the fridge, from the refrigerator, after that if it is left over the environment, if it is left over the table, the temperature of the watermelon is less than the atmosphere. What happened after certain period of slowly the heat transfer takes place from atmosphere to the watermelon. So that watermelon temperature is getting increased, slowly getting increases with respect to time. So this is also unsteady state heat conduction. It is called Newtonian heating. Newtonian heating. When you take the same copper ball from the furnace, same spherical shape you can take. If it is comes out with 800 degrees centigrade, after if it is left over the environment or water bath, whatever it is, the temperature start to reduce. Here it is Newtonian cooling. So for cooling as well as heating, this lumped heat capacity is applicable when the internal conductance, internal resistance or internal conductive resistance is assumed to be negligible. So today so with this I am closing the session. Actually the conclusion of today's session, we seen the what is mean by unsteady state heat conduction, what are the difference between unsteady state heat conduction. Actually in steady state heat conduction, heat transfer vary with respect to heat transfer does not vary with respect to time, but in unsteady state heat conduction it can vary with respect to time as well as location. And we have seen the governing, we have seen the applications of lumped unsteady state heat conductions like cooling of IC engines or pasteurization of milk, freezing of foods, like that. After that we have derived the governing equation by assuming a body is left to the environment. Finally we derived the governing equation. Then we have seen the characteristic length, how to find the characteristic length for simple shapes such as plates, cylinders, spheres and cubes. Then finally we have seen what is Biot number and Fourier number, what is the significance of Biot number and Fourier number. Biot number signification, it can give the ratio between internal conductive resistance to convective resistance. By means of Biot number we can identify whether the system comes under lumped heat capacity system or not. Because Biot number is less than 0.1, then it is coming under lumped heat capacity system. Fourier number is used to identify, or it used to find the degree of penetration of heating or cooling effect through a solid. So thank you. I am closing the lecture. Thank you very much.